Hey guys, here we go with the second video. It might be three, it might be just two. And this is the part where we're going to learn about what we call sigma notation. This big Greek letter that kind of looks like an E is called a sigma, and it's a Greek S, and it stands for summation. Like because the word summation starts with the letter S, and sigma is like an S, so it's very clever. This is almost always called sigma notation. So really this ought to be like sigma and then summation in parentheses because no one really calls it summation notation. But basically what it means, this means the sum of all the A sub i's. This I here is called the index. That's why it starts with the letter I. The sum of all the A sub i's from I equals this number to that number. So basically it's like you start at whatever the bottom number is, that is the first term you use, and you keep adding all the terms between whatever this number is and whatever that number is. This is called, these are kind of both the indices, and this is just your kind of term of the series or the sequence. So these are all like the terms in the sequence, and this is telling you to add up all of those terms between this index and that index. This is going to be easier when we see an example, which there are plenty of in these notes, including on the next slide. So here it says find the following sums. So this one says start when the index is 5. Here's your term. Start when it's 5 and end when it's 5. So this is just one term. 2 plus 5 cubed. 5 cubed is 125. That's 127. That was pretty straightforward. This is maybe a better example right here. So we're going to start when the index is 1, and then we're going to do when the index is 2, 3, 4, and then we're going to stop because this tells us where to stop. So it's like start at 1, stop at 4. So the first one, when I is 1, the first term is going to look like this. 3 times 1 plus 1 squared. This I would call A1 right here, first term. When the index is 1, then we add, because the sigma means sum, the second term, which is going to be when I is 2. So we do 3 times 2 plus 1 squared. And then this would be A2. Then we're going to add the third term, 3 times 3 plus 1 squared. This is A3. And then the last term is 3 times 4 plus 1 squared. That's A4. Now you don't actually have to have these outside parentheses here, but I'm just putting them there so we can differentiate between the terms. So let's see, 1 plus 1 is 2. 2 squared is 4. 3 times 4 is 12. 2 plus 1 squared is, 2 plus 1 is 3. Squared is 9. Times 3 is 27. This is 4 squared, which is 16 times 3 is 48. And then 5 squared is 25. Times 3 is 75. And then you add all these up. 70 plus 40 plus 20 plus 1. 70 plus 40 is 110, 130, 140. 149 with these two. Plus 13 is 162. 162. So this expression is equal to the number 162. These sigmas, particularly when there's numbers in them like this, are always equal. They're always going to be equal in numbers. So that's basically what we do. Remember, this tells you what the function, quote unquote, is, and this is like the I you start with, and this is the I you stop with. So here's some more practice. I'm going to skip this for now and let you guys do these on your own. What the hell I'll do. So this one's fairly straightforward. It's just the index. In this case, the index is K. It could be K or I or N or whatever. Here they're using K. K is 1, so it's like whatever the index is, you cube it, and we start when the index is 1, and we go till the index is 5. So that's 1 plus 8 plus 27 plus 64 plus 125. And that, I'm going to use my calculadora to answer that question. 1 plus 8 plus 27 plus 64 plus 128. I get 228. 228. So that's how we do this one. Again, it's the same process. You just plug the index in and you keep going up until you get to the top number. This time the index starts at 0, which is fine. It can start wherever you want it to. So we get -1 to the 0 times 5 to the 0 plus -1 to the first times 5 to the first plus -1 to the second times 5 to the second plus second plus -1 cubed times 5 cubed plus -1 to the fourth times 5 to the fourth. So this one I know is just going to be 1. Anything to the 0th power except 0 is equal to 1. So this is 1 times 1, which is 1. 5 to the first is 5. -1 to the first is -1. So this is -5. -1 squared is +1. And 5 squared is 25. This one's going to be negative because it's raised to an odd power, 125. And this one is positive, and 5 to the fourth is 625. And that equals, this is 500 plus 26 is 526 minus 5 is 521. Make sure I did that right. 500, 25, 26, 21. Yeah. Now, this one, I can see my index here starts at 8 and it ends at 11. So I get 2 plus 1/8 plus 2 plus 1/9 plus 2 plus 1/10 plus 2 plus 1/11. And that equals the four twos add up to 8, and then I got to add up all the fractions. 1/8 plus 1/9 plus 1/10 plus 1/11 is, you can make that into a fraction if you want, but you don't have to. It's 8.42702 repeating. And just for funsies, it's also equal to 33,371 over 3,960. Either one of these answers would be okay. I kind of like the fraction better, but it's a pretty miserable fraction. So these next two pages have, these pages have, this is like a trickier concept to write a sum using sigma notation, because again, you have to figure out what's a sub n equal to. And then you can start your index wherever you want. I usually start it at 1. There's 1, 2, 3, 4, 5, 6, 7 terms, so it's going to go up to 7. And these, if I look at this and think about it, these are all powers of 2. This is 2 to the first, and this is 2 to the second, and this is 2 cubed, and this is 2 to the fourth, this is 2 to the fifth, this is 2 to the sixth, and this first one you can think of as 2 to the 0 if you want. So basically it's 2 to a power, but like the first term, since I is 1, I don't want it to be 2 to the I, because 2 to the I would give me 2 for the first term, and the first term is actually 1. So if I want to get a 0 as my first exponent, I got to do I minus 1. You can think of it like the exponent is 1 less than the index for each term. This is the second term, but the power is 1. This is the third term, but the power is 2. Fourth term, but the power is 3. So I always want the power to be 1 less than the term I'm on, and that's how I get this. This one looks like it's just even numbers. I'll start my index at 1 again, because I just always do it that way. So I equals 1. I got 1, 2, 3, 4, 5 terms, so it stops at 5. So how do I write the a sub n here? Well, I would say that these are even numbers. And this is 2 times 1. And this is 2 times 2. And this one is 2 times 3. And this one is 2 times 4. And this one is 2 times 5. So it's just 2 times the index. And so I can write that as like 2i, because the index is called I. Well, like the way that we get these alternating terms is we do -1 to a power, like, and then so like if I do -1 to the I, when I is 1, this is negative, and when I is 2, it's positive, and so on and so forth. In this case, it's always going to be either -1 to the I or -1 to the I plus or minus 1. We can say +1. And then you just see which one works. So for the first term, I want it to be negative. And -1 to the first is negative. -1 to the second is positive. So I want to leave it like this. And generally, we write that -1 term first times 2i. And you can always check these, like by plugging in 1, 2, 3, 4, 5, and see if you get these numbers. I'm confident that you will here. So to me, like the hard part about this is usually writing the expression for a sub n. And there's not too many of these I'm going to ask you to memorize or figure out, but like even numbers, odd numbers, powers of 2, maybe perfect squares or something. We'll see a couple more examples here. This is just the number 3 over and over again. So here, start my index at 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. 1, 2, 3, 4, 5, 6. Yeah, there's 9 of these. And here, a sub n, this one's actually easy. A sub n is just 3. Doesn't matter what the index is. The term is always 3. So, boom, done. And now this one is a bit trickier. But I can do it in a similar way. Start at 1. This time, this dot, dot, dot here, let me redo that because that was terrible. That means, the dot, dot, dot means that it means that there's an infinite number of terms. Like it just goes on forever. And these you see a lot in AP Calculus. There are different kinds of series called Taylor series and power series. This is a power series. And the trick is what you do to indicate that it goes on forever is at the top, you say from I equals 1 to infinity. Like I want all the indices starting at 1 and going up. So I don't actually have to count the terms here. I just know the dot, dot, dot tells me that it's an infinite series. But again, how do I write a sub n? And the way to do it here is to think of it like there's powers of x and there's numbers below them. This is really x over 1, and that's x squared over 2, and x cubed over 3. The fact that the power and the thing it's divided by, the denominator, are the same means that whatever I get for the power, I just put that on the bottom too. So here, the first term, the power is 1, and the number it's divided by is 1. For the second term, a2, a2, the power is 2 and denominator is 2. For a3, the power is 3 and the denominator is 3. For a4, the power is 4 and the denominator is 4. Basically, a sub n is just x to the n over n. Because the index, you can see right here, and the power and the denominator are all the same number. 3, 3, 3, 4, 4, 4, n, n, n. And here, since I'm using I for my index, I would call it x to the I over I. And these letters are not vastly important. I tend to use I every time because it's pretty common. If you wanted to use, say, from n equals 1 to infinity down there, instead of from I equals, you could write n, n, n here, you could do that too. As long as you're consistent and it makes sense, then you're in good shape. What else we got here? Just some more examples, more examples, more examples. I think that this one, like the ones where you have to write the sigma notation, are probably more difficult. So I'm gonna leave you guys. I'll do this one. Oh, this one I should do because it's tricky. So 1, 2, 3. There are 5 terms. And the tricky part here are the denominators, I think. So this is the first term. And this number is 3 more than the index, and this number is 4 more than the index. And this number is 3 more, and this number is 4 more. And this number is 3 more, and that number is 4 more. So like whatever the index is, this first number is the index plus 3. So I write that as n plus 3. And this second number is the index plus 4. So n plus 4. The denominators are not as obvious. I don't know if you all can see this, but to get from this one to this one, you multiply by 2. And to get from this one to this one, you multiply by 3. And then from this one to this one, you multiply by 4. This one to this one, you multiply by 5. And that process is, if you may recall this from like a random class years ago, it's called factorials. And what that ends up giving you is this is 1 factorial, this is 2 factorial, 3 factorial, 4 factorial. Factorial is indicated by an exclamation point. Basically, factorial, which is indicated by a number with an exclamation point, like 3 factorial is 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. And 10 factorial is 10 times 9 times 8, so on and so forth. So that's what's going on the bottom there. And you might be like, well, how was I supposed to know that? And the answer is, you weren't supposed to know that. But I just told you, so now you know it. So this is a kind of a handy thing to keep an eye out for. It's like one of those very common patterns. So I'm going to stop this video now. It's probably kind of long. And if there's a request for it, I'll happily do the rest of the practice problems in another video. But for now, I'm going to hold off on it. Let you guys look at the homework and stuff and see if we can finish it. Bye.